Have you ever stopped to think about what's actually going on when you send an email or when you stream a movie? It feels like magic, right? But really, it's all built on just a few core principles. So today, we're going to pull back that curtain and demystify the entire journey, from one single cable connecting two computers, all the way to the massive data centers that basically run our world.
So here's our game plan. We're going to build this thing from the ground up. We'll start with the simplest connection possible, then we'll look at how data actually gets delivered, explore the different blueprints for building networks, see how big businesses scale them up, and finally check out the physical roads that all this data travels on. Sound good? Let's go.
All right, first things first, the basic connection. Before we can even talk about the global internet, we've got to understand the most fundamental concept of what a network is at its absolute core.
So let's just ask the big question right out of the gate. When you strip away all the jargon about clouds and Wi-Fi, what are we actually talking about when we say the word network?
It's honestly this simple. A network is just two or more devices hooked up for one main reason: to share stuff. That could be sharing a file or maybe access to a printer or, an internet connection. The key takeaway, the most important word there, is sharing. That's it.
To make this really stick, let's use an analogy that everybody gets: the postal system. The network itself is the whole shebang: the roads, the mail trucks, the addresses on the envelopes. It's the entire infrastructure that makes sure a letter can get from point A to point B. Just keep that idea of roads and addresses in your head as we go.
Okay, so our devices are connected. Great. Now, how do they talk to each other? Well, just like with the mail, there isn't just one way to send a message, right? You need different delivery methods for different situations.
And this table breaks down the four main ways perfectly. First, you've got unicast. That's one-to-one, just like sending a private DM. Then there's multicast, which is one-to-many, but only to people who actually want to hear it, kind of like a Zoom meeting. Broadcast is the opposite. It's one to everyone in the area, like a school PA system. You're going to hear it whether you want to or not. And finally, Anycast is really clever. It's one to the closest. It's perfect for finding the nearest, fastest server to give you an answer.
Now here is a fantastic example of how networks are getting smarter. That old, noisy, shout-at-everyone broadcast method, it wastes a ton of resources because it forces every single device to stop and listen. So the modern internet protocol, IPv6, just gets rid of it completely. Instead, it uses a much more targeted form of multicast. And that's absolutely crucial for a future that's going to be filled with billions of smart devices. It's all about making the internet quieter and way more efficient.
So we know how the messages get sent. Now let's talk about the different ways to actually connect the devices in the first place. You need a plan, right? An architectural blueprint? In the world of networking, we call these blueprints topologies. And here's why that blueprint matters so much. The old bus topology on the right, what a nightmare. If that one main cable broke, the entire network went down. Poof, gone. The modern star topology on the left is way more reliable. Every single device connects to a central switch. So if your cable fails, it's just your problem. Everyone else keeps working much better. Now in modern data centers, speed is literally everything. So they use a blueprint called spine and leaf. And the logic here is it's beautiful. Any server is always exactly 2 hops away from any other server. It goes from the server to its leaf switch, and then from the leaf switch to the spine backbone. That's it. It makes performance incredibly fast and, even more importantly, totally predictable. So, to sum it all up, you pick your blueprint based on what you're trying to do. For a reliable office, you use star. For a company that has a main HQ and a bunch of remote branches, you use hub and spoke. And for the crazy fast needs of a cloud data center, you use spine and leaf. Simple, right? The design just follows the function. So, building a small office network is one thing, but what about a gigantic corporate campus or a hospital? For that, you need a really structured, layered approach so you can manage everything without it turning into total chaos. The gold standard for this is the 3-tier model. You start at the bottom with the access layer. That's literally where you plug in your computer or your phone. Those switches then connect up to the distribution layer, which kinda acts like middle management. And finally, everything funnels into the core layer, which is just a super fast backbone whose only job is to move data as fast as humanly possible. The best way to think about this is like a hospital. The access layer is the patient's room. It's where the user is, where they plug in their devices. The distribution layer is like the nurse's station on that floor. It's the middle manager that gathers all the traffic from the rooms. And the core? That's the main data center, probably in the basement. The powerful, high-speed engine that connects all the floors together and gets you out to the rest of the world. Okay, so we've got our connected devices, we've got our delivery rules, and we have our architectural blueprint. But that brings us to the final piece of this whole puzzle. What are the actual physical roads from our postal analogy? What does the data actually travel on? Well, the two main wired options are copper and fiber. Copper cables use pulses of electricity. They're cheap, they're easy to work with, but they've got a distance limit of about 100 meters. Fiber optic cables, on the other hand, use pulses of light. They're completely immune to electrical interference and can send data for kilometers, which makes them perfect for connecting buildings or even entire cities.
So really, it all just comes down to a trade-off. Copper is your go-to for affordable, short-distance connections, like at your desk. Fiber is the absolute champion for speed and any long-distance connection. And then you have wireless, or Wi-Fi, which gives you ultimate convenience, but it has to operate in a pretty noisy environment and needs a bit more security.
And here's a quick vocab check on a word you've probably heard a million times: broadband. Your standard office Ethernet connection, that's baseband. The entire cable is dedicated to just one signal at a time. Your cable internet at home, that's broadband. That one cable is divided up into lots of different channels, which lets your TV signal, your internet, and your phone all use the exact same wire at the same time.
So there you have it. From the super simple idea of just two connected devices to the delivery methods, the blueprints, the scaling models, and the physical roads data travels on, we've basically built a network from the ground up, piece by piece. The only real question left is, now that you have the blueprint, how will you see the connected world around you differently?